Okay.
Is it okay if you just take a screenshot of the actual text area where you just show the console instead of the terminal? That if it's printing out hello.
That is at the terminal.
Well, there's two different.
Yeah, but it shows them both at the same time, right?
No.
Like this.
I'm not talking about this up here. I'm talking about instead of doing it down here in the bash, are you okay if we do it in where it's running? That makes sense.
Oh, so you're clicking run here?
Yeah.
Instead of typing in the commands like we did in class?
I ended up doing it that way, but he just so he knows.
Well, don't hit run. Type in the command gcc test.c and then /a.out, and then take a screenshot of this with it running down here. All right. So let's talk about some of our primitives here. So we've already seen output to screen. It uses a function called printf. And printf takes in what's called a formatted string, followed by comma delim params. Something like this. And let me show you what I mean by that, because we're going to look at outputting the screen, inputting the screen, creating arrays today, random numbers, and generating memory. Okay, so if I go back in here, I'm going to go ahead and I'm going to create a couple of variables. I'm going to say int a is equal to 5, int b is equal to 7. Now, if I want to print these two values out, I can print them out one at a time. Now, historically, the placeholder for a, I would say something like A is %d, B is %d, D is for decimal value. Most modern compilers, it also work for %i for integer. All right, %d is your decimal value. Now notice I have a big long string here. A is %d, B is %d, but the %d's are placeholders. So following the formatted string, I can put, in this case, it's expecting me to put the value that this guy's the placeholder for and the value that this guy's the placeholder for, separated by commas. So I'll say A and B, like that. And then I'll go ahead and run and compile, or compile and run. And there's the A is 5, B is 7. I forgot to put the kick it down to the next line dealy thing there. So there's the A is 5, B is 7. All right, that's if you're going to output the same type. All right, now what about strings? What are strings? So in our programming languages we've learned about before, what is a string? Not a trick question. It's a big collection of characters. All right. Now in our modern languages like Java, if we create a string, we say string s is equal to hello. We can then ask s what its length is. Correct? Well, in C, so if we say a string is a collection of chars, I'm actually going to throw an extra word in here. It's a terminated collection of chars. These guys are implemented as char arrays, something like that. All right, so we have to kind of give a starting point of how long the string might be. So as an example, I might come in here and I might say char s 50, something like that. So I have a string name s that can hold up to 50 characters. All right, and then maybe I say hello world. Actually, I want to see if this is going to actually work in this version of the interpreter or this compiler. Before I see anything else, otherwise I'll introduce a couple other functions.
I've been spelling hello world for so long that I spell hello world ending with a W.
Why does that happen? All right, so yeah, this worked. Now, there's some magic that's happening in here. So first of all, what I'm going to show you is we're going to go ahead, and this guy is a char array, right? This is equivalent to, in Java, me saying something like char array s is equal to new char array 50, and then this is me filling that up with the characters hello world. Now I mentioned that this is actually a terminated string, and let's see what I mean by that. Because if we create an array of 50 buckets, that's like I have 50 little squares next to each other in contiguous memory. What does contiguous memory mean? Memory in a row. So if this starts at bucket 100, bucket 105 will be the fifth element in there. Okay? So, am I using 50 characters here? I have room for 50 characters. But now when I printed this out, so %s is our placeholder for strings, it only printed out hello world. If you want to see that, here, I'll just throw a little LOL in there. So we should see LOL right next to it, not 50 spaces down the line, right? Does that make this larger down here? Let's see if I can make the text bigger down there, but maybe no. Oh, wait. Does this let me do it? Oh well, I'm not going to mess with it. We'll just say it's big enough. If you happen to come across how to make it bigger, let me know and I'll make it bigger. All right, so I'll go ahead and compile it. We'll run that guy, and notice there's just that single space in there for LOL. So the %s thing here seemed to know where this string hello world finished. Make sense? Okay, it didn't give me 50 total buckets and then throw LOL after that. And we want to see how that actually works here. So I'm going to go ahead. We're going to create a little for loop. So I'm going to say int I. Let me just show you a quick error message that you'll get if you do something. For int I equals 0, I is less than 50, I plus plus, something like that. And then I want to print out a specific character in that string. So I'm going to say printf. What would you guess is the placeholder for a character? If %d or %i is for an integer, %s is for a string, what do you think a character might be? %c. And, yeah. It's like, that's absolutely wrong. It's actually %q. No. It is %c. And we'll kick it back a line here. And I'm going to go ahead and I'm going to print out s at bucket I. Okay? Which I don't really like that syntax, but I'll show you an alternative to it that makes you feel like you're really a C programmer here in a few minutes. This would be like C for Java people, right? This looks basically like Java at this point. Now, this is actually going to give me a, I don't know if it's going to be an error or a warning. Error. So it's saying for loop, initial declarations are only allowed in C99 mode. So somewhere in there was a newer version of C. So we're talking about the kind of, when we first learned about C, we talked about C kind of came out in the late 60s, like 68 or so. And then for years and years and years, we were dealing with that same version of C. And throughout the the decades, there might have been some slight updates. Well, in 1999, there was a major update to C that allowed environments to work a little bit differently. We've always taught that a for loop has an environment that comes with it, not until 1999. So prior to 1999, we were not allowed to embed a variable in here. That makes sense? So I would have had to define int I prior to this so that I could set the variable there. So what did this actually create? We aren't able to have a local environment associated with a for. So I now belongs to, from this point forward, inside of main. That's its scope. All right. So go ahead and save this. Run that guy again. All right. And then we'll run it. Gotta scroll up here to get to our actual stuff. So there's my hello. Remember, you see I'm kicking it down the line each time. Then world. And then something but nothing, right? Okay, it printed out 50 things, the next stuff in line because of the way I created my character array. So what does this line right here do? Let's actually write it in because there is a little bit different. So I'm going to say, let's say we have char whatever, just roll with it. I'm going to show you something here in a second before I go any farther here. So we know hello world. I'm actually just shortening it so I don't have to count as high. We're just going to have it say hello. So that's bucket 0, 1, 2, 3, 4. I'm interested in is what actually lives at bucket 5. I've mentioned that strings are terminated character arrays in C. So I'm going to go ahead and I'm going to just get rid of this for loop for a second. I'm going to steal that line. Right, and I'm going to print out bucket 5. Now we've already seen bucket 5, right? So what would we expect to have printed out here? I'll go ahead and throw an LOL after this just so we know it actually gets printed out. We've seen a whole bunch of spaces, right? Before. Oh. Pac-Man button JPEG. So there's this blank space and then LOL after that. But we're really interested in what that blank space actually is. It's a special symbol. Now, how are Booleans represented in C? We've all read chapter 1 and 2 from the book, right? I assigned us to read chapter 1 and 2 from the book like week 1 or 2, something like that, right? Are you lying? Might you be lying?
I might be misremembering. It was like 2 weeks
ago. All right, that's fine. Anybody know how they represent Booleans in an old language? When we think of Booleans, we think of true and false, right? Zeros and ones. Zeros and ones. So they're represented as integers. Okay? So they're actually represented as a byte type, but let's just call them integers for us. So I want to know what that character is actually equal to. In C, we have a termination character. Anybody know what that termination character is? So we've seen some special escape characters, right? We've seen, what is \n?
New line.
Okay, so that's new line. What is \r? Seen this one? Yeah, so most modern terminals treat \n as a carriage return, then a line feed. This is carriage return, \n is new line feed. But typically \n nowadays gives you both. It's a power move, right? Where historically, if you wanted to do both, you would have to have two different things there, \r then \n. All right, so we have some different escape characters. Well, \0 is the string termination character. Okay, it's a special character that when we use %s with printf, it walked through our string, starting at the base address of it, until it finally hit a \0. And at that point, it knew that's the end of the string that this guy holds. Even though this guy has a space in memory of 50 buckets, it only went to bucket, whatever, 8 or 9, whatever it was. Make sense? That \0 gave us the... so let's look at the evidence of that. So I'm going to go back in here, and I am going to print out an integer, a Boolean. And this Boolean is going to be whether or not bucket 5 is equal to the char \0. We couldn't see it out on the screen, but we want to know whether it's equal to that char, right? There's 1 for true. All right, so Booleans in C. One is true, 0 is false. All right, and if I go to bucket 6, that should not be what's there. I can't imagine it just escapes the rest of it, so it should be a... Oh, it does escape the rest of it. Nice. Go to S at bucket. There. Now, what did I just do there? Explain to me what the current code does. And forget about this line right here. Let's just look at the... This wouldn't have flown in Java. What do you think? Well, what's this line doing? To the first parts of it, right? And then we just saw that the current compiler does the \0 for the rest of the string, not just at the next bucket. Okay, fair enough. What's this guy doing? Specifically, what's this guy doing? That's an array index out of bounds exception in Java, right? C seemed to be very happy with it. No problem with it. Remember that old slide with what was the problem with C++, and that was it empowered the user to make a bad programmer? Java has a whole lot of error messages and exceptions and stuff like that that throws in our face whenever we make little mistakes. We just walked off the end of an array. C's fine with it. And we do notice here, just because I wanted to prove the point, that bucket 50 is not the \0. So, because it does the escape all the way to the end of the string, it seems like, in the modern compiler. Off the end of the string, it didn't. So I did a... this is actually, have you heard of something called a buffer overflow? It's kind of one of like the hacking techniques or something like that. That's what they do. They get the base address of something, typically something that's part of the operating system, walk off the end of it, and then it can inject code into the operating system if it's in the right place. Because the language like C lets us do that. Okay? Now, I don't like this syntax for... and actually, this is kind of evidence for us. I just gave you an example that really, this looks very much like Java, right? It kind of feels array-y. And that's okay. If you want to write things that way, that's okay. But as a C programmer, you really want to get into this mindset of we are manipulating memory. So we're going to write, I'm going to introduce another function to you here. we're going to use a function called Malloc. How many of you have ever seen Malloc before? At least in some Google search or something like that. Now, Malloc is old school new keyword. Stands for memory allocate. That's what Malloc stands for. All right, so the Malloc function takes in a size of memory to create. And then it returns base address of that memory. Now, when we're in Java, we might say something like, okay, if you want a character array of size 50, you might say, all right, I want a char array called AR, and this guy's going to be a new char array of size 50, and we rely on Java to figure out how much actual memory needs to be created to build one of these dudes, right? Now tell me, how much memory needs to be created to build a 50 character array in Java? How big's a char in Java? In C, it's a byte. C uses ASCII. What does Java use? Unicode. So ASCII is 256 unique characters. Unicode is 65,536 unique characters. So it uses a short 16 bits. Uses 16 bits. All right. So the size of a char in Java is 2 bytes. So how much space do I need to store 50 of those? 100 bytes. Right? So Java is going to go and say, new keyword, go and find me 100 bytes. That's how it's going to translate that for us. Now, in C, we want to think with memory. So the equivalent of this in C is we're going to create a char pointer. Remind me, what's a pointer? What are pointers?
Doesn't it refer to a spot or a memory address?
So this is a primitive type. Primitive type capable of holding a memory address. An int is a primitive type capable of holding an integer. A char is a primitive type capable of holding an integer because it actually holds a Unicode value. A double primitive type capable of holding a floating point number. A pointer is a primitive type capable of holding a memory address. Okay? So, I'm creating a char pointer named AR. And this guy is going to be equal to whatever is returned by Malloc. And for Malloc, I want, and I'm going to go ahead and throw, because this is going to come out by default. I'll put this part in a second. So I'm going to allocate some memory. How much memory? 50 times size of a char on that particular system. For C, that's going to be 1 byte. Now, by default, Malloc produces a void pointer. So kind of a generic pointer. We're trying to stick it into a char pointer, so we're just going to go ahead and typecast that real quick and just say, that guy's actually a char pointer. Okay, so let's go into our code here. So rather than write it this way, we're going to go ahead and we're going to say we want a char pointer s, and this guy is going to be equal to Malloc. I'm going to show you what the error message looks like here in a second. This guy is going to be equal to Malloc of 50 times size of char. Let's get rid of this stuff here for a second. Do a printf %p \n s. All right, I'm going to go ahead and build that real quick. Notice we get this warning. Incompatible implicit declaration of built-in function Malloc. What it's saying there is I haven't heard of that guy. So what we can do down here is like, oh, well, this should work. I'm going to go ahead and open the man page for Malloc. And we're going to see that Malloc is actually included inside of something called standard library. Standard library.h. So we're going to need to include this guy at the top so we have access to that. I'll go ahead and try to compile it again. Now it's happy. It did put a void pointer inside of here. It didn't require us to actually cast it, but it's a good idea to cast it. When you want to do math with it, it'll take the correct size steps, and you'll see what I mean by that in a minute. Go ahead and run that, and does that look like a memory address to you? Memory address, all right? And our placeholder for memory address is %p, pointer. Cool? All right, so now, what if I say s plus 2? A little bit different memory address. Still a memory address. It's called pointer math. Okay, so when we added 2 to that, we added 2 times the size of a void pointer. We don't want to rely on that. Okay, a void pointer might be different sizes in different languages, or in different architectures, different operating systems. I specifically want to say, look, this dude is a char pointer. Okay, and then I'll go ahead and do the s plus 2 just for the sake of whatever. So there's a memory address. Now we might say, oh, well, why would we want to do math with pointers? Just because it looks intimidating and all that good jazz. Well, let's go ahead and put something into our string here. So I'm going to go ahead and say s is equal to hello. And then let's go ahead and let's print out s. Big money. There we go. So there's my hello printed out. So notice that my char pointer called s was just assigned the result of allocating a bunch of memory. Base address of that guy. And then I went ahead and I put hello into that, which went ahead and did the \zeros and stuff for me. This actually would not have worked in a very old version of C. We would have had to use something called string copy. So if I do man strcpy, I think. Yeah, so we would give it the address of what we want to copy into. So if I would do this. Oh, and this is in string.h. So I would have to include string.h in order to have access to this. But this would have done the work of copying hello into s and then doing the \zeros for me. Now it kind of does it for me, so we're a little bit at the mercy of how recent the compiler we're working with is and what it deems to be requiring C99 flag or not. So we'll keep it, I guess, simpler for whatever. Okay. So we saw this printed out hello. Now I'm going to go ahead, I'm going to print out the pointer s plus 2. So that should be bucket 0, bucket 1, bucket 2. So that should be an L, correct? This is going to give me the memory location of that L. I'm going to say, give me the character. So I'm going to say, give me the character at that memory location. So I want star s plus 2. That is the value at that memory address. S plus 2 will be a memory address, right? S is a memory address, so S plus 2 will be another memory address that's 2 char pointers down the line, size of char down the line. Star S says, give me the value at that place. Let's do pointer syntax. Remember when I first taught you Java, one of the things I said that a lot of textbooks in Java say that pointers don't exist in Java? Then we spent some time showing that pointers are all over the place in Java. What actually didn't exist in Java is a specific syntax for working with pointers. C and C++ have a syntax for pointers. So we have star gives the value at an address. Ampersand gives the address of a value. Okay? And I'll show you these two things here in a second. So I'm going to say, I want to print out a character. What character? The value that lives at this memory address. So S plus 2 is going to give me a memory address. Then I'm going to say, give me the value at that memory address. Make sense? Now this guy is just going to be a memory address, and I'm printing out the pointer. So this should give me an L at whatever the memory address ends up being. Oh. There's my L at crazy memory address. But we know that S plus 2 is going to be the same. So this S plus 2 will come out to the same value as this S plus 2. But in this case, I'm saying, give me the value that lives there. And that guy will fulfill the placeholder for a character. This guy is going to say, give me the address that is the base address S plus 2. Give me that pointer, which is a memory address. Go ahead.
How did you get the Malloc thing to work? Because I tried doing me and Malloc and mine's still giving me the warning.
Okay, so let me show you a little bit about that. I was just talking about the different syntax. So I'm going to, let's just kick it down the line. So forget about the first thing that prints out. I'm going to say int a is equal to 5. I'm going to do a printf, and we're going to do %d at %p. And this is just formatted string, right? So I'm going to print out a decimal followed by a pointer, a memory address with the word at in between. And then I'll kick it down the line after that. The decimal I'm going to print out is going to be a, because a is an int. The memory address I want to print out is the address of a, ampersand a. That will give me the address of a. Even though, I mean, when we create an integer, we're creating a little storage location in memory, correct? We know that's happening. Even though we didn't do any memory-specific stuff here, we know that 5 lives somewhere in memory, and that place in memory is pointed to by the address of a. In a language like Java, we can't extract that piece of information because there isn't a syntax for working with pointers in Java. But in C, I can say, give me the address of A. Show me where that guy lives. So there's a 5 at crazy memory address. Similarly, if I want to say int pointer b is equal to the address of a, I could replace this a here with star b. Star b says, give me the value at this memory location. B holds the address of A. Similarly, I can just print out B here. So B holds the address of A, so B is equivalent to ampersand A. Star B is equivalent to A. This says, give me the value at the memory address B. Memory address of B happens to be the address of, well, happens to be A. The address of A is 5. The value at that address is 5. So we should see the exact same output here. There's the 5 at, we got a little bit different output because we ran the program a second time, so it was assigned to a different memory location. If you want to see them at the same time here, I'll just copy this line. And we'll print out A and address of A. So we'll see those are synonyms for each other. Exact same values. All right, does that make sense? So asterisk says give me the value at a memory location. Ampersand says give me the address of a value. Okay, so let's do some math here then. So we already saw what we can do with our pointer arithmetic here. So I went ahead and filled my string up with hello. Then I'm going to go ahead and we'll just say int I is equal to 0 for, actually, why don't we say this? While s plus I, the value at that position, is not equal to a 0, or the termination character, a \0. So while this value, that is the value that lives at this memory address plus this offset, the value at that memory address, while that guy is not equal to the escape character, we'll go ahead and do a printf. We're going to print a single character, %C. What character are we printing? The character that lives at s plus I. And then we need to say I plus plus in here. When this while loop finally ends, that means we're sitting at the character \0. So I'll go ahead and just do a printf \n to kick it down a line. So there's our hello. So this is the cool kid's way of walking a string. Way cooler than that stupid square bracket syntax, right? We're walking through memory, byte by byte, or size of char by size of char. All right, questions about that? All right, so let's just walk through this real quick. What are we doing right here? We're allocating some memory. How much memory? 50 times however big chars are in this operating system. That's going to give me some memory. That's going to come out as a generic void pointer. I'm going to say that guy's a char pointer. That way when I take leaps, it's char size leaps. When I add 1 to it, I'm adding 1 char size step. So we'll store it in a char pointer. I'm actually not 100% positive, Mike. I feel that in this compiler, you probably could leave this off and it would look at the type and walk the correct size steps. But proper programming would say, look, I want this to be a char pointer, so I'm going to go ahead and cast it to be a char pointer. It'll come out as a void pointer. All right. Now I went ahead and I filled it with hello. And that filled it with HELLO, followed by a whole bunch of termination characters. Then I created a counter variable, I. And this guy I'm using as an offset. So S is the base address of my string. When I want to get the very first character, I go to the base address and I add 0 to it. Puts me right at bucket 0. Give me the character at that. Now I becomes 1. So the next time through, I go to the base address, I add 1 to it. That's the next character. Print out that character. Add 1. Next time I go to the base address, I add 2 to that. Gives me the next character. So on and so forth. I keep doing that as long as the current character we're looking at is not the string termination character. And then I just went ahead and threw a carriage return on there. Carriage return line feed to kick it down to the next line. Make sense? So if next class we had a quiz for doing a little pointer arithmetic stuff, we could handle that. All right, so now let me show you how to do a couple other things. What if I wanted to create an integer array that could hold 100 integers? How would I write this differently? That would be int star AR. This guy's going to be equal to an integer pointer, Malloc, 100 times size of int. Now, what if I want to go ahead and fill that guy with random numbers? Well, we have a function called rand. And let's, just for the sake of argument here, let's do random numbers between 1 and 100. 0 and 100, just so we don't have to do anything extra. So I'm going to go ahead, we're going to create another for loop. So we'll say int I is equal to 0 for I. Actually, I just need to say for int I. And I'll say I is equal to 0. I is less than 100. I plus plus. And we'll go ahead and say star s plus I, or if you're wimpy, you can say s at bucket I. That's what the wimps would do. Say s at bucket I.
You need to AR, not S.
I did, thank you. This is going to be rand mod 101. That'll give me 0 to 100. These two lines do the same thing. I don't care which of the two you use, but I'm telling you it will benefit you moving forward in this class if you get used to this syntax. Because we're going to be working with memory quite a bit. So getting used to working with memory will be a beneficial thing. All right, so I'll just comment out this guy here. This should fill this up with a bunch of numbers between 0 and 100. And then I'm just going to go ahead just right after that guy, just to save some time here since we're out. I'm just going to do a printf %d \n, and we'll print out the value at AR plus I. So this should show 100 random numbers between 0 and 100. Oh, it doesn't like my other I because I defined it again. Just started over there. So there's a whole bunch of random numbers. Make sense? All right, so I'll go ahead and paste this current version of the code up on Slack so you have as a starting point. Your assignment for Wednesday is to create an array, fill it up with random numbers, then write an insertion sort. And I gave you a link to Wikipedia for insertion sort or something along the lines of insertion sort. So you'll get some practice of moving stuff from one memory location to another memory location as it bubbles up. All right, questions, comments, concerns, bribes. All right, see everybody on Wednesday.